Swayam Prabha. Digital India. Educated India.
Hello everyone. Today I am starting the lecture 2 of the module 2. So, taking reference of the earlier classes, that is the last class that I discussed, especially the rectangular plate simply supported along all edges, formulations were done, that is a general formulation for any type of load was given, and then for a particular two cases that we have seen, one is uniformly distributed load over the entire area of the plate, and second one is a patch load, that is uniform load, but it is distributed over certain rectangular area which is less than the plate area. So, two cases we have seen the formulations. We derive the equation of deflection surface, and from there we could derive the expression for bending moment, shear force, S shear, etc. Then we also discussed the corner reaction, especially it happens for simply supported plate. When the corners are not restrained, it has a tendency to lift up the corners, and this happens due to twisting moment along the two adjacent edges, which introduces a upward reaction at the corners. So, that case we have discussed, and the expression for corner reaction is also derived based on the simple mechanics. And then we discussed one problem, numerical problem to find out this deflection. Now, I want to proceed. The partially distributed load formula is known to you. From that, I want to proceed to find out the deflection surface due to concentrated load. So, let us see what we will cover in this lecture. We shall use the expression of deflected surface of partially loaded rectangular plate, simply supported along all edges. That formulation which was ready to us will be used for deriving the expression of deflection of the plate, rectangular plate simply supported along all edges, subjected to concentrated load and concentrated couple. So, concentrated load is very common in bridge actually, when a bridge deck which can be modeled as a plate, vehicle wheels are moving on the bridge, and as a result of this vehicle movement, the wheel loads are transferred on the bridge deck as a concentrated load. So, concentrated load formulation we want to show today, and code has given, actually if you refer the reinforced concrete design code, then you will find that effective weight method is given for concentrated load, but here we will derive the exact expression with the help of plate theory. Okay. So, this is our first objective in the lecture. Secondly, we will discuss a special method by using the direct delta function. Direct delta function is a special mathematical function or a operator you can call, which simplifies the calculative effort significantly. So, that function how it can be used for discrete load, this concentrated load, that will be discussed in today's class. Then line load, that is a strip type of loading acting on the plate. The practical example are seen in case of brick wall constructed over a slab. So, brick wall along the length or along the breadth of the slab will impose a load which can be considered as distributed in a line, distributed like a strip loading. So, that loading imposed due to brick wall construction or any other manner on the plate can pose some difficulty, because the distributed load actually it is not a distributed load, but distributed along only one direction. So, we shall see how the line load or strip loading can be tackled or handled using our known expression or theory. Then we shall solve some numerical problem. Okay. So, let us see, recapitulate the earlier expression that we have derived. We have shown you earlier that a plate, a rectangular plate of length A and width B subjected to a patch loading of rectangular area, uniform intensity, and the load covers the area alpha cross beta. So, alpha is the length of the load and beta is the width of the load. So, alpha is parallel to the longer direction of the plate and beta is parallel to the shorter direction of the plate. Okay. Now, here other two parameters are important to locate the center of gravity of the load. The centroid of the load here is, coordinate of the center of the load is xi beta with respect to the origin taken at the left hand top corner. Okay. So, with respect to this point, we have the x coordinate as xi and y coordinate as eta. So, these are the parameters that we know. So, it is not necessary that the load will be symmetrical always, it may be eccentric also. Then you will find that xi is not equal to a by 2. If xi is equal to a by 2, then center of the load is exactly at the center and you will get this symmetrical load distribution if xi is a by 2 and eta is b by 2, but this may not happen always. So, load may be eccentric over the bridge deck. Specification is there, say wheel load must have a certain clearance from the edge of the footpath. So, if this minimum clearance is maintained, then you will find that load is not always symmetrical with respect to x and y axis of the plate or not symmetrical in the plate. So, due to unsymmetrical distribution, again you will find that twisting moment is becomes predominant, but with this formulation that we derived today, you can handle symmetrical as well as unsymmetrical distribution of the load without any difficulty. So, for that loading case, we found the deflected surface of the rectangular plate, and the deflected surface, the general formulation requires the Navier series, and Navier series is given by double summation a m n sin m pi x by a sin n pi y by b. So, this is actually the Navier series. So, in the Navier series, a m n is given by 16 p as some function of xi eta alpha beta. What are these parameters? Let us see. Xi and eta, these are the coordinates of the centroid of the load, and alpha and beta is the length and width of the loaded area. So, these are the parameters which gives a function f which is dependent on xi eta alpha beta. Then p is the total load acting on the plate. So, if the density of the load or intensity of the load is uniform, say q naught, then p will be q naught into alpha into beta. So, that is p total load. Then your this other parameters m and n are the harmonic numbers, or actually these are integers. So, half wave number you can tell. If m is equal to 1, you will get 1 half wave along the x direction. If m is equal to 2, you will get 2 half waves along the x direction. If m is equal to 3, you will get 3 half waves in the x direction. Similarly, if n is equal to 1, you will get 1 half wave in the y direction. If n is equal to 2, you will get 2 half waves in the y direction, and so on. And these are the parameters involved in AMN, coefficient of deflected curve. Okay. Now, QMN actually is found from this AMN is actually dependent on QMN in original formulation if you see, but QMN for that case is found as 4 p a b pi square alpha beta mn sin m pi xi by a sin n pi eta by b sin m pi alpha by 2 a sin n pi beta by 2 b. You can easily observe that xi and eta are the coordinates of the centroid of the load and alpha and beta are the length and width of the load. So, knowing this quantity QMN, we can find AMN, and once AMN is found, we can find the deflection. But question arises, what is f xi eta and alpha beta? Okay. Now, let us see the expression for deflection. Again I have written here, substituting Mn in this place, and we get this is the expression for deflection Wxy, where f function of xi eta alpha beta is nothing but sin m pi xi by a sin n pi eta by b sin m pi alpha by 2 a sin n pi beta by 2 b. So, these are the functions of this f xi eta alpha beta, which is found from this expression. All right. Now, let us see how we can obtain the case of concentrated load, how we can formulate the expression of Wxy for concentrated load starting from this expression. Okay. So, the expression that we have earlier derived, from that we will start the influence of concentrated load acting on the rectangular plate. Rectangular plate simply supported, SS means simply supported, in short, along all edges. So, that is our boundary condition. So, if I see the plate, we have this as the x axis and this is y axis, and this can be taken as the origin. Now, we have a patch loading of uniform intensity. The area of the patch loading is alpha cross beta, and center of gravity of this patch loading is here. The x coordinate is xi and y coordinate is eta. Okay. So, these are the parameter involved, and intensity of the loading is q naught, such that q naught into alpha beta will give you the total load P. Now, with the help of this expression, we have derived earlier the expression of deflected surface. Okay. The expression of deflected surface was that Wxy double sum m varies from 1 to infinity and AMN sin m pi x by a sin n pi y by b. So, this is our original expression for deflected surface, where AMN is equal to 4 QMN divided by DAB pi to the power 4 m square a square plus n square by b square whole square, where the QMN is here. Actually, the patch loading is there. Patch loading is q naught, which is of constant intensity, and then if we integrate between the limit xi minus alpha by 2 and xi plus alpha by 2 for in x direction and eta minus beta by 2 lower limit and eta plus beta by 2 upper limit of this function sin m pi x by a sin n pi y by b dx dy, we get a expression which will be now using. We will be using to find the deflected surface for concentrated load. So, this expression is given by this 4 a b pi square alpha beta m n sin m pi xi by a sin n pi eta by b sin m pi alpha by 2 a sin n pi beta by 2 b. So, this is our QMN. So, once the QMN is known, then AMN is known, and after knowing AMN we can find completely the deflected surface. Now, to find the effect of concentrated load, we shall assume that the area alpha cross beta is very small. So, that is possible when the limit in the limit alpha and beta goes to 0. Then the total load Q naught into alpha beta is concentrated at a point. This point is defined as the centroid of the load. Okay. So, this indicates that we have to take the limit of this function. Only QMN is of concern, because if we know QMN carries the variable which is actually the location of the load and the extent of the load. So, if I take the limit of QMN as alpha and beta tends to 0, then we will be able to find the appropriate value of QMN and hence AMN that have to be substituted in the expression for W to get the deflected surface of the plate. Okay. So, now let us see how we can find the limit. Okay. So, in the limiting case, when alpha and beta tends to 0, then load is a point load is P, which acts at coordinates previously we have the distributed load. Now, instead of distributed load we have the concentrated load acting here, for example. So, P is acting here and this location of P is defined by the coordinates xi and eta. That means, if you see a section and this is simply supported slab, of course, this is simply supported slab. If I see the section, then you will find, okay. Let me see the section of the plate along the load. You will find the load is acting here P if this section is shown along the longer direction. If this section is shown in the shorter direction, then you will find this length is A. If this section is shown in the shorter direction, you will find this is eta and the length of the plate in the shorter direction is B. Okay. So, we have the expression for QMN. QMN was 4 P A B pi square m n and then sin m pi alpha by 2 a sin n pi beta by 2 a 2 b, then multiplied by sin m pi xi by a and sin n pi eta by b. Okay. And alpha beta, this parameter were also there in the denominator. Okay. Now, take the limit of q m n as alpha and beta goes to 0. Okay. So, if we take the limit, we know that very important formulation in our calculus, differential calculus, this sin say a x, limit of say a x as x tends to 0 is equal to 1. Okay. So, that formulation is known to us. Based on that limit, now let us take the limit of this function. You will get that if I alpha and beta goes to 0, that means if I take 4 p a b pi square m n alpha beta, then limit alpha goes to 0, then I write sin m pi alpha by 2 a. In the denominator again I will write m pi alpha by 2 a. That means, I have to multiply this function by m pi alpha by 2 a. So, that I will show you later. Let me write the limiting value. So, again limit beta tends to 0, we will get this sin n pi beta by 2 b, and here n pi beta by 2 b. So, that limit we have written, and then sin m pi xi by a into sin n pi eta by b. Okay. So, we have actually divided this function by m pi alpha by 2 a and here n pi beta by 2 a. So, to keep the equality of this expression, we have to multiply this function by m pi alpha by 2 a and n pi beta by 2 b. Okay. So, you can see now from this a b will get cancelled here, then 2 is 4, that 4 will be also cancelled, alpha beta will be cancelled here, m n will also be cancelled, and pi square will also be cancelled, and this value is actually 1, this value is also 1. So, ultimately we get the limit of q m n as alpha beta goes to 0 is nothing but p is there and sin m pi xi by a sin n pi eta by b. So, that is the limit of this function q m n. Once the limit is found, then we can find the a m n. So, expression a m n is now found out with the help of this limiting value. So, a m n will now turns out to be 4 p sin m pi xi by a sin n pi eta by b divided by d. D is the flexural rigidity of the plate, pi to the power 4 m square by a square plus n square by b square whole square. So, this is the value of a m n. Once you know the a m n, then deflection surface is completely known. So, deflection surface is now for a concentrated load situated at a distance of xi from x axis and eta from the y axis, we have the expression for concentrated load. Okay. So, let us see what are the expression for concentrated load. So, deflection now becomes W x y and limit we have found out earlier. So, 4 p we can substitute and sin m pi xi by a sin n pi eta by b divided by d a b pi to the power 4 m square by a square plus n square by b square whole square and sin m pi x by a sin n pi y by b. So, we have derived the expression for deflection surface of the plate, rectangular plate simply supported along all edges subjected to a concentrated load. The location of the concentrated load is governed by or defined by two variables xi and eta. So, in a plate actually there may be number of concentrated load. For example, a bridge deck, a panel, a deck panel of a bridge subjected to vehicle loading. Okay. There may be two axles in general. So, two axles on the both sides right and left you will get this wheel. So, wheel loads are imposed and you can see if this is say P 1 in the same axle, of course, the load is same, then P 2 P 2. So, if this is the direction of motion you will see that the load imposed on the plate is concentrated load and it is a moving load. So, concentrated load formulation is very important for especially for bridge deck analysis when the wheel loads are treated as a concentrated load. The expression for W is found out and based on which we can find out the expression for m x minus d and expression for m y okay. So, this is the deflected surface of plate subjected to concentrated load P at okay. From that expression we can arrive that m x m y and if required other values can also be found out. Then q x, the shear force q x will be minus d and q y minus d. Okay. So, all the stress resultants are found out after finding the deflection. Deflection is the basic quantity from where we can differentiate and we can find the quantities of interest, the bending moment, even the twisting moment also you can find. Twisting moment is equal to minus d 1 minus nu cross derivative, that is the twist curvature will come into picture. Okay. Now, let us introduce a very interesting method to tackle the problem of concentrated load, that is by use of direct delta function. Okay. Now, in many situations the forcing function, whether it is a plate problem or even any other problem, may not be continuous. For certain point it is significant or certain location it is significant, for other locations or other places there is no importance of that load. So, that happens in many physical problems. So, in that situation suppose a real axis is taken which extends from minus infinity to plus infinity, and on the axis at certain point certain impulse is there. Okay. So, this impulse is defined only at this point, say x is equal to a, if this is x axis and this is y axis. But at all other points except a, there is no value of or there is no function does not exist. So, that means this type of function impulse can be defined by a direct delta function, which has the significant here x minus a is 0 for x not equal to a, but x is equal to a, it still remains undefined and the magnitude is very high. But restricting this limitation, we will now use this direct delta function to represent the concentrated load on the plate. So, equivalent distributed load in the plate subjected to the concentrated load, we can write as, suppose the load is acting at the coordinate here, x coordinate is xi and y coordinate is eta. So, the q x is now expressed here like that. The direct delta function has very important property, use of which the calculations are simplified. So, the properties of direct delta function that is used to simplify the calculation is this. So, direct delta function defined at point x is equal to a and multiplied with a function say f x, any function, and it is integrated in the real line between two limits minus infinity to plus infinity, any limit, then the integral will be just the value of the function evaluated at this point x is equal to a. So, in case of concentrated load acting on the plate, if I write like that, say any function which is a function of x y in two dimensional problem, and integration is carried out along the x axis and along the y axis in infinite domain, then we get say direct delta function is situated here. So, double integration will result just the value of the function evaluated at this coordinate, okay, xi and eta. So, if a function say a function is defined f x y is equal to say x square plus x y plus y square, say a function is defined. Now, if I want to integrate this function with a direct delta function say x minus 1 and y plus 1 for example, and limit say limit you can take any limit, okay, say minus 10 to plus 10, finite limit or infinite limit, and here say 10 again minus 10 to plus 10. Okay. Just to explain this use of direct delta function, what will be the integral? Integral will be the value of the function evaluated at the point where the direct delta function is significant. Okay. So, here it will be evaluated as x is replaced by 1 and y is replaced by minus 1. So, if the function is given with this function is defined as x square plus x y plus y square, then value of the integral will be 1 plus 1 minus 1 plus 1. Okay. So, the answer is 1. So, now you have understood the use of direct delta function. So, if I use this in the evaluation of QMN in the plate problem. So, QMN is defined as double integration q x y sin m pi x by a sin n pi y by b dx dy in the limit say 0 to a and 0 to b. Now, if a concentrated load acts at a coordinate xi and eta, then we will write p double integration 0 to a 0 to b, then it is acting at coordinate x is equal to xi and y equal to eta, then sin m pi x by a sin n pi y by b dx dy. So, the QMN is now for the plate problem is very simple now. It will become P into the function is given by sin m pi x by a sin n pi y by b, and it is evaluated at x is equal to xi and y is equal to eta. So, integral become sin m pi xi by a sin n pi eta by b. So, this is same what we obtained earlier in the limiting process. Now, once the QMN is obtained, obtain AMN. AMN is given by this as 4 p sin m pi xi by a sin n pi eta by b divided by d a b pi to the power 4 m square by a square plus n square by b square whole square. After getting AMN, we obtain the deflection function as w x y as the double summation of this AMN sin m pi x by a sin n pi y by b, and you put this index for summation. Okay. So, this is the procedure for handling the concentrated load in the plate. Okay. Now, let us see what happens in case of line load. So, if a line load is acting in the plate instead of your this concentrated load, then also it is possible to obtain this QMN. For example, we have the plate line or strip loading. Suppose a rectangular plate which is simply supported along all edges. Simply supported along all edges, and for example, we have this loading, a brick wall is constructed or any other load which is imposes a strip loading, okay, whose intensity is say q per unit length, and this line load is imposed at x coordinate is xi, and it is running full along the y coordinate. So, in such cases the load q x y is defined as q, okay, then direct delta function x minus xi, where the q represents the intensity along the line. So, this is the load representing a strip loading on the plate. So, with the help of this representation, now we can obtain QMN as this sin m pi x by a sin m n pi y by b, and then it has to be multiplied by dx dy. Now, replace this q x y by q, q is a constant. So, we can take it out. Okay. Then we have this value sin m pi x by a sin n pi y by b dx dy multiplied by direct delta function x minus xi. Okay. Now, integration with respect to x will result a value say q sin m pi xi by a, then the integration with respect to y remains. Because of the property of direct delta function, we have found this integral with respect to x very easily by replacing x by xi. This integral can be carried out, and finally, QMN can be obtained as q into sin m pi xi by a, and this is minus b by n pi cos n pi y by b, then you put the limit 0 to b. Okay. So, after simplifying this you can get completely q m n, and then you proceed to find a m n and then deflected surface a m n. Now, let us discuss what happens if a concentrated couple is acting instead of concentrated load. So, let us now discuss the case of concentrated couple. Say a rectangular plate shown here, this is x axis and this is y axis. A concentrated couple, see M is acting here. The location of couple is also defined by the coordinate xi and eta. So, at this point the couple is acting and the length of the plate is a and width of the plate is b. Okay. Now, to handle such problem, what we do actually, we the couple is acting along the x direction. So, what we do actually, we replace, suppose I am drawing a section of the plate, okay, where couple is acting, we replace this couple by two equal and opposite forces. Okay. Two equal and opposite forces, say P, acting at a distance del xi, such that P into del xi is equal to m. Okay. Now, the external moment, what is done? The external moment is replaced by two equal and opposite forces acting d xi apart as shown here. Okay. Now, if we decrease d xi by a very small value to a very small value, say if we decrease d xi to a very small value while maintaining the original value of the m p into del xi, we must proportionately increase p. This procedure is identical with replacing p by m by d xi. So, p can be replaced by m by d xi. Okay. Now, here at this point you are getting a downward load p, and at this point you are getting upward load p. So, at the point xi or at the location xi, downward load is p, at the location xi plus delta xi, the load is upward and its value is p. Okay. Now, we know for the concentrated load P, the expression for deflection, which is given by this earlier expression that was 4 P, okay, 4 P sin m pi xi by a sin n pi eta by b, then d a b pi to the power 4 n square b square whole square, then a function of x and y, which is nothing but sin m pi x by a sin n pi y by b. So, in one case, in downward loading case, we will replace p by m by d xi, okay, and the location of this xi will replace it as a xi and eta remains as it is. But when we come to the neighboring load at a distance of dxi apart from xi or a location defined by xi, then we replace xi by xi plus delta xi and eta remains as it is, because it is acting along the x direction. So, it is defined as this. Now, if I see this is the function of say whole function, if I see, so p is replaced by delta xi, okay, and then we can write this deflected surface as your the m by delta xi, okay, function of x y xi eta for downward load, and for upward load a function x y xi plus delta xi and eta. Okay. And the summation process is there, of course, the summation process you cannot ignore this. Then in the limit when d xi tends to 0, we get the effect of couple. So, in that case it is written as m, and if I see the limit of this as del xi tends to 0, del xi tends to 0. So, what is this? From the definition of derivative we can write this is the derivative of the function, say derivative of the function x y xi eta. So, that means for concentrated load and concentrated moment, the expressions that is derived for concentrated moment is due to limiting process of the expression derived earlier for concentrated load. So, now W x y can be written as A m d f d xi okay. So, for concentrated load this is the expression for the deflection, where m is the couple that is acting at a certain location xi and eta, and x y are the functions of the location where we want the deflection, and total function. So, f xi eta x y has to be differentiated with respect to xi, with respect to location. That means, first you derive with differentiate with respect to x and then put the value of xi. So, that is the process of finding the this problem of or solving the problem of concentrated load. That means, in expansion form we can write W x y is 4 m, substituting the earlier expression we will get and because of differentiation of your sin m pi xi by a, you will find that cos function will be appearing. So, cos m pi xi by a, then you are differentiating with respect to xi because the moment is acting along the x axis. So, sin n pi eta by b will remain unaffected, and other function with variable x and y will appear as it is. So, due to differentiation this function earlier it was sin m pi xi by a. So, it is changed to cos, and the coefficient that is coming out of the differentiation is divided or multiplied with the coefficient existing with this expression. Okay. Then other important parameter, that is wave number square, that was also be existing in this. So, this is the full expression for the deflected surface of the plate subjected to a concentrated moment at location xi and eta. Okay. Now, let us give an example of this. Okay. So, here a square plate of size 1.5 meter by 1.5 meter simply supported along all edges and carries a concentrated load at the center. Okay. The magnitude of the load is given, and the maximum bending stress not to be exceeded 230 MPa, this condition was given. So, we have to find the shear force distribution, the S shear distribution as well as your this plate thickness. So, first you calculate D, the flexural rigidity of the plate, substituting the value of the quantity. If it is a steel plate, then E is 2 into 10 to the power 5 and H remains in millimeter, H cube, then 12 1 minus mu square, mu is 0.3 we have taken for steel, this value is 18315 H cube, the unit is Newton millimeter. Okay. So, D is found. Now, Wxy, because it is a concentrated load problem. So, it is given, take only one term, m is equal to n, m and n equal to 1. So, there is no need for summation. So, we write it because it is acting at the center. So, xi by pi a by 2 divided by a, that is pi by 2. So, sin pi by 2 is 1, again along the y direction you are getting also sin pi by 2. So, because of the central location you are getting all sin function as sin pi by 2 divided by 1 by a square 1 by b square whole square, because we have taken only one terms. Okay. Now, since it is placed at the center, so m x is equal to m y, and after substituting this, of course, here the sin function will be there, location sin m pi x by a, sin n pi y by b. So, m x is equal to m y, and you will get this value as p by pi square 1 plus nu sin pi x by a sin pi y by b. Again at the center x and y equal to a by 2. So, you are getting maximum bending moment is p by pi square 1 plus mu. So, the stress that is produced due to bending moment is maximum at the center, and it is given by 6 m max divided by a square. Now, given condition is that delta max should not exceed 230 MPa. So, based on that you can find out the thickness H. The thickness H here comes out to be 22.7 mm. For this problem and given data, this thickness comes out to be this. Now, if we want to calculate the shear force distribution, that is the S shear, the expression for S shear along x is equal to A H, because it is symmetrical, it will be same, equal to minus d after substituting the value of derivative, you will finally get the result as S shear value as 85.89 for sin pi y by b. This unit will be Newton per mm. So, if I see the distribution along one edge, this edge I have taken as x is equal to a edge. So, distribution is sinusoidal, you will get the S shear distribution like that. Okay. This is the distribution of S shear along x is equal to a, but since it is symmetrical, you will get similar distribution along the other edges. So, the problem is solved because we know the deflected function of the plate due to concentrated load. Using this deflected function and taking derivative up to third derivative, we can then obtain the S shear along the edges, any edges you can find out. Okay. So, thank you very much.